All right. Thanks SVI for inviting me to give a talk at this wonderful event. My name is Jiheng Zhang, and I'm from EPI and Hong Kong University of Science and Technology. Today, I'll share with you guys some of our recent research on mechanism design based on a structured DAG. I think these slides need very little introduction for this audience. I just want to quickly make 2 points. So first of all, blockchain technology, take a Bitcoin for example, roughly on average, every 10 minutes, there's going to be a relatively big block produced by one of the miners over the world. And it's a 1 megabyte of size, which contains around 4,000 transactions. This leads to a TPS of around 7. So what is so great about this system is that it has been proven to achieve decentralization and security. However, there is still room for improvement. So this is very relevant to what we're going to talk about today. So first of all, it will be nice to scale up the capacity by an order of magnitude that will enable a wide range of applications. There are a couple of minor issues. For example, the latency. Currently, we have to wait for around 6 blocks. Each takes 10 minutes for a transaction to be confirmed after that's being packed in a block. But it takes even longer depending on the transaction fee for a transaction to be sitting in a so-called mempool. And also, as the hashing power has been increasing over past years, the crypto puzzle has become more and more difficult to solve. So the consequence is that it's very, very difficult to create a block. However, the reward of creating a block is huge. So this creates a huge volatility in return of miners' income, and that forces all miners to join large mining pools, leading to the concentration of mining power. The last one is that the transaction with little fees really have no chance, because in this system, a transaction involves $1 million of money and a transaction for Starbucks coffee that will be treated in the same way. And it's very difficult for transactions involving small amount of money to give large transaction fees. So how are we going to increase the chance that transaction with little fees can also be processed? So we hope that our new design can make contributions towards solving these problems. Here's some idea that has already been piloted. The idea is that to break the big block, which contains thousands of transactions, into smaller one, for example, just contain one, and to let different miners to create it over almost continuously over the time. But the question is, how are we gonna reach consensus? It's so good about this design because it allows parallelism, right? So that can potentially scale up the capacity. But in order to reach consensus, the idea is to use this directed acyclic graph. This idea has been piloted by IOTA. The idea is that the validity of each block or each transaction is justified by the number of future blocks that are willing to point to it either directly or indirectly. This requires pretty much constant weights update of all the blocks in the system, which is computationally expensive. So we actually have some idea, taking this one step beyond. Here's a hint. So we think that there should be a structure in the DAG, and each line here represents a miner. Okay, so this is the main keyword that I'm going to be talking about today, which is a structure in DAG. So in order to describe the structure in our DAG, let me first describe the contents of our block, which is the vertex in the graph. So for the block, here's the table for block size. We first need to have 3 pointers. Each is a SHA-256-bit hash, 32 bytes. The first pointer needs to point to the miner's previous block. And this will help us form the peer chain, as demonstrated in the previous slide. The second one will be pointing to a special type of block, which we call milestone block. And I'll be talking about these 2 types of block in the next slide. This will help us to embed the Nakamoto chain in the DAG. The last pointer needs to point to one of the regular block made by another peer. This will enhance the connectivity, thus reduce the latency. There's something called overhead. So the overhead is defined to be the size of the header over the size of the whole block. Think about it, if we put one transaction, which is about 400 or 500 bytes, in one block, and that will be in the message part. So if you calculate the overhead, it's going to be roughly around 17%. But however, the overhead diminishes as you put more and more transactions in one block. So here's a table, but we think that it's a worthwhile trade-off just by simply putting one transaction in a block, as you will see later on. Think about if we develop a system with 1,000 TPS, for example. This would roughly lead to the accumulation of data about 10 terabytes per year. So with 17% overhead, this is just going to be 12 terabytes. Well, if 5%, this is just going to be 10.5 terabytes. But it's for designing such a system, I don't think this 17% is a big deal. We have actually more important problems to solve in this system. Here's the two types of blocks. There are regular blocks, which lead proof of work for creating a block. For regular block, you need the leading X bits of 0, and for milestone block, it should be more difficult than leading Y bits of 0. So regular block brings the reward of creating this block and the reward of transaction fee that this transaction is willing to give you. For milestone block, there's going to be additional bonus that we'll talk about in the reward scheme. So very important thing to note that while a miner is preparing the block and hashing on it, the miner wouldn't know what kind of block it will turn out to be. In terms of implementation, the speed of producing milestone is fixed in our system, on average every 10 seconds. Difficulty is automatically adjusted to accommodate the changing of hashing power. And the total number of blocks being produced per unit of time is going to be 1,200. So the upper bounds of the capacity of the design system. Here's the illustration of the structure in our DAG. And I highlight this red chain. And for each parallel line, this is the peer chain. That represents the sequence of blocks is produced by each miner. So we call it the peer chain. And for each peer, we have the peer state, which is simply the most recent block created by this peer. And this peer state will be very useful in one of our mechanism design, which is called the transaction assignment that I'll be talking in a few slides. If you look at the red one, this is what we call Nakamoto chain or milestone chain. This chain will help us to reach consensus in the same way as how Bitcoin blockchain reached consensus. If you look at this highlighted blue arrow, this is actually the third pointer that needs to point to another peer's regular block. This helps us to enhance the connectivity. Take a look at the milestone chain. It allows to be forked, right? If a milestone chain being forked and those milestones not on the longest chain will be treated in the same way as regular block when we construct our ledger. Here's another look to understand the structure. I have grouped the blocks into several groups. You can see indicated by K, K plus 1, K plus 2. It's called level set. So what is a level set? So basically, if you look at each milestone, actually the milestone pretty much confirm the whole DAG. By confirm, I mean if a milestone confirm a block, then there's going to be a directed path that you can follow from this milestone to a block. Okay, so the level set is defined by two consecutive milestones. So if you take this highlighted level set K plus 2, for example, so that is all the blocks that's being confirmed by the fourth milestone, the milestone made by a miner 4, but however not confirmed by the previous milestone. Okay, so that is level set. So mathematically, we're going to introduce the minimum amount of mathematical notation just for clearly explaining our algorithm later on. So level set is denoted by S of B, BM and BM prime. BM is the current milestone, BM prime is the previous one. And a C of BM denotes all the blocks that's been confirmed by this block. Okay, so to just draw the comparison between our structure and the blockchain, the Bitcoin blockchain. So essentially, each level set plays pretty much the same role as each big block in the Bitcoin blockchain. But however, the difference is in Bitcoin, each block of 1 megabyte size is created by one miner, one of the miners, roughly every 10 minutes. But however, if you look at the level set is being created by all the miners over the network continuously throughout the time. So they can continuously create a block and broadcast the block. So that will make the P2P network more efficient. Okay, so we need to talk a little bit about the mempool. So think about here, we have 5 transactions in a mempool. And there are 4 miners. Which one do you like? Which transaction do you like? There are transactions giving only $1 of transaction fee. There are transactions giving $100 transaction fee. And obviously, everybody likes transactions with high fees. So this is what's going to happen, right? Due to the broadcast delay, I'm not talking about malicious miner. I'm just talking about miners who want to make most money out of that. And it could happen that in a very short amount of period, that each miner, not knowingly, the others working on that, put this transaction in their block. Okay, and if you see that miner 4 didn't pack this transaction, it's probably because he produced that block like much slower. So he learned that others has been already processed that before he create the next block. So this caused 2 problems. Okay, so first of all, it's the waste of the capacity that we have been trying very hard to scale up. And the second, this is very vulnerable to attack. I mean, cheap attack. So normally, when we think about attack, the attack like malicious user need to own and using a certain percentage of the hashing power. This is very expensive to own and very expensive to use hashing power. However, in this case, a malicious user with the intention of waste a large portion of the capacity just need to continuously broadcast transactions with attractive fees in rapid succession. Then he can achieve the objective. So our idea is to use the peer state that we just introduced before. Not everybody can process every transaction in a mempool. If a miner wants to process a transaction, the miner needs to do this check. So take your miner state, which is the hash of your most recent block, and that transaction, you concatenate these 2 and hash it. And if the hashing results 256 bits 01, you convert that into a number between 0 and 1. If that is less than C times the percentage of your mining power, you can process it. Otherwise, you cannot. Okay, so this actually plays a role of partition, not exact partition, but partition the transactions in a pool to different miners. Then obviously C is a parameter that needs very careful modeling selection. But the nice thing about this idea is that, first of all, this is verifiable. So everybody produces a block that contains a transaction, and this can be verified by other miners, whether you violate the rule or not. So this is verifiable. Second one is that the miner's hashing power can be inferred in a consensus way from the peer chain and the level sets. So we have our algorithm specified in our paper. So the choice of the parameter C is actually very difficult. So we need some modeling analysis. And later on, I'll show you some of our analytical results and showing how to choose C. Because if you choose C to be too small, then a transaction would have little chance to be produced at any given time, and need to wait for the changing of state of all the miners, and thus leads to a long latency in mempool. Okay, this is transaction assignment. So next, let's discuss the protocol that how miners across the network can maintain a DAG. So first of all, what should you do when you receive a block? So suppose Alice has her local DAG, which is, as the notation that I introduced before, C of BM, and BM is her highest milestone, and C of BM is all the blocks has been confirmed by this milestone. Well, if the height of BM is too small than her peers, then similar as in Bitcoin, Alice needs to download the missing level sets from her peers. Okay. The next is that when Alice receives a block which points to some block that is still missing in Alice's local DAG, what Alice should do is to ask for these blocks from her peers. Okay, so after these 2, and also when you get those blocks, you need to perform this so-called topological sorting in a way that when you add block, you can add block one by one, such that when you add each block, all the blocks this block points to are already in your local DAG. Okay, now let's talk about how you're going to add one block. If you want to add block B into your system, you need to check its syntactic validity. So basically whether the block header pointers are correct, and of course whether the transaction it contains satisfy the condition that we specify in the previous page. If that is not syntactically valid, you just discard it immediately, even without broadcasting further. Otherwise, you're going to take that into your local DAG. But there's one more step for you to check. So you need to check whether this block B is a milestone. If that is a milestone, and if the height, we use eta to denote this height. If the height is longer, is bigger than the height of your local DAG, then you need to perform a major switch. It's what I write in the last block. So let me explain the major switch in detail. Okay. So imagine this is Bob's DAG, and this is pretty much the DAG of all Alice's peers. Okay. So this is the same as what we have seen before. And you see this pending set. So pending set is a set of all blocks that so far hasn't been confirmed by any of the blocks, any of the milestones on the longest milestone chain. That's pending set. Okay. However, due to broadcast delay, Alice might think the world is like this. So what is that? So if you look at this blue milestone, before Alice received the milestone by miner 5, the very last milestone, very last red block. Okay, so Alice may have received the blue one first. So in Alice's view, that the chain that connects to the blue one, that's the longest milestone chain. And everything else is in the pending set. However, if Alice receives a block B, and if this B turn out to be a milestone like illustrated here, then Alice needs to check whether this B's height is higher than the highest milestone in her local DAG. And in this case, it's higher than that. Then Alice needs to switch her view of the DAG and to make her local DAG exactly same as Bob's. Okay, so this is a major switch. Next, let's talk about what we should do when we create a block. In order to create a block, what you need to do just fill in the table, right? First of all, you need to find a transaction that you can process according to our transaction assignment rule I talked before. And you're going to put that into the message part of this block. Next, you need to prepare 3 pointers that as we have specified. Third, you just apply hashing function on this block by varying the nonce until the required pattern is satisfied. Once you create a block, you broadcast it through the P2P network. Okay, so there's one thing very important to note is that in this creation process, similar as the process of receiving a block, we only care about the syntactic validity, which means that we don't care whether the transaction it contains is valid, there's no double spending, it doesn't conflict with other transactions, because this will be taken care of later when we convert our DAG into a ledger offline, after we have reached the consensus about the DAG. There are a few issues in this design. First of all, in the syntactic validity check, there's no mathematical rule that we have to force each miner to point to her most recent block. That means a miner can be naughty. I have my own miner chain, but I don't point to my most recent one. I point to a previous one. Okay, so there's no mathematical rule against that. This will lead to peer chain fork, which is problematic later on. We'll design a reward scheme to prevent any of the 3 to happen. The second one is that some miner can be lazy. So yes, the syntactic validity only require me to point to a previous milestone in my second pointer, right? So why do I need to work so hard to point to the most recent one? I don't need to. I can point to just a milestone. It could be remote. It could be ancient milestone. Okay? But this will cause consensus to be failed. The third one is similar. So why do I need to point to a most recent block by other miners? Well, if I know of some block, I just keep pointing to that, and I'm lazy, and it means less work for me. So this will cause connectivity to be broken, and that leads to a very long latency time. And so to solve that, we need to design a reward scheme. To present our reward scheme, I need to first introduce how are we going to build a local ledger. take a look at this. So this is an illustration of 5 miners with their blocks. And what I highlighted in gray is a level set that's confirmed by the red block, the milestone. Okay? So we need to, first of all, sort this because the DAG is not a fully ordered set. So how are we going to sort it? We're going to use a very standard post-ordered depth-first searching to sort that. And the advantage of this sorting algorithm is that it keeps, strictly keeps the chronological order of blocks on a peer chain. And second one is that approximately keep the chronological order of all blocks. Not exactly, but approximately. Okay? Once we have this one, what are we going to do is to order all the transactions, TX1, TX2. So now let me describe you that how are we going to build a ledger from that. This is after we have reached consensus about the DAG. So every miner or every peer would have the same set of DAG, and they construct the ledger from the same set of DAG. So the algorithm is pretty simple. The algorithm is like this. So we use L to denote the ledger and U to denote the UTXO. And in our implementation, we use the exact same unspent output transaction, unspent transaction outputs as the Bitcoin. We're going to check whether transaction K plus 1 is valid. Well, this validity check is about double spending, is about whether the inputs are from the current pool of outputs and things like that, and also includes signature. So if that is not valid, you're going to discard it immediately. But if that's valid, you can update your ledger by adding this transaction, because essentially a ledger is a list of transactions. It's a list of ordered transactions. You can append this to the end of your ledger. And also you need to update your UTXO. You basically take the new outputs from this transaction into the collection of your UTXO, and of course remove the input of this transaction. Okay, so this is about building a ledger. So now let's talk about the reward scheme. Okay, there's going to be 2 slides about reward scheme. And first of all, we haven't talked about how miners can redeem or can receive their reward. Okay, and we also talk about the size of a block, and when we talk about overhead, actually I scratched the peer information. Because in order to form the peer chain, the simplest way to implement that is to simply throw a signature or through some kind of ID into a block. Like let's say that will be roughly 65 bytes, but that will increase the overhead. Actually, in our implementation of this design, we remove such a need. And the idea that how we can do that is the follows. So this is the illustration of one peer chain, let's say Alice chain. Okay, so everybody's chain starts from Genesis, which is a special type of block with a trusted setup information. And every miner, your very first block will be the so-called registration. You don't put a transaction in this block. What you do is that you put a public address in this block to where you want your future rewards to be put into that address. Okay, so that's called registration. And every once in a while, it's all up to your own, the miner's own choice. Every once in a while, the miner can throw a redemption block. This is pretty much same as registration, but it's a redemption because it's not the first one. What the redemption block does is very simple. The redemption block will collect all the rewards since last redemption and put the rewards all together in the address that's specified in the previous redemption block. As simple as that. And how are we going to recognize the peer chain? Yes, you can fork that chain, but we're only going to recognize the peer chain by the redemption blocks. Last question is that what if miners being naughty and put another redemption block on a fork? Well, in that case, that will be resolved by milestones. The advantage of doing this is that first, as I said, there's no peer ID or signature needed, so we can save space in the message. Eventually, we save storage. And another is that like Bitcoin uses this so-called Coinbase. Think about if you design a high TPS system, say 1,000 blocks per unit of time, that means that UTXO will be accumulating 1,000 per unit of time. And then you end up with too many UTXOs in your system. Okay, so that's why we designed this system. Okay, next we're going to talk about the reward. The reward is like this. Okay, here's a table. As I said, that for a milestone block that not on the longest milestone chain, that will be treated in the same way as regular, so I put regular plus. So first of all, note that if a block is a forked block on peer chain, then there's nothing, zero reward, and even a transaction won't be recognized. Okay, so that will force each peer to maintain their own peer chain. Second one is that if you get just a regular block, not a milestone, you still get a reward. You get a fixed reward per block and the transaction fee that the transaction in this block is willing to give you. So this would encourage a miner to still broadcast the newly mined block, even if that's not a milestone. Okay? So if you look at the last column of this table, this is called a bonus. Yes, if the block you created is a milestone, and if that turned out to be a milestone on the longest chain, you get some bonus. This serves as the incentive for miners to try their best to append their block, which upon the time of creation, not knowing the type, but try best to append this to the most recent milestone. If you look into the bonus is going to be a percentage of all the blocks. For example, if there's 10,000 blocks in your level set, then for 10,000 blocks times R is the reward for single block, and times a certain percentage. This is a relatively huge reward for those miners who are lucky and contribute to a effective milestone. Okay, we hope this kind of reward scheme will prevent the three issues that we mentioned earlier on. All right, let's talk a little bit about modeling analysis. It involves some heavy mathematics, and you're encouraged to take a look at our paper. So remember this transaction assignment rule, right? The hash after being converted to a number between 0 and 1 needs to be less than C times the percentage of miners' hashing power. Well, how are we going to choose C, right? By a very simple calculation, you can draw the conclusion that a transaction is not workable for any miner in a system with probability e to the minus c. So if you choose c too small, that means the transaction has to wait in the mempool for a long time to be qualified to be processed by a miner. Okay, so we have some analytical results. So basically, see together with the network condition, with broadcast delay function, that will lead to the percentage of waste and the queuing latency, infection latency, and the secure latency. So let me explain. The waste is the waste that I described before. That is, multiple miners happen to process the same transaction, leads to the waste of the capacity. And the queuing latency is actually the waiting time in a mempool. Infection latency is that once a transaction has been packed in a regular block in the DAG, it takes time for this transaction to be confirmed by the very next, to be first confirmed by a milestone. So that's what we call infection latency, because we analyze this latency using an infection model. The last one is called secure latency. This is the same as the secure latency in Bitcoin. That is, after one milestone has already confirmed that, how many more milestones do you have to wait to really confirm this transaction? So now let me show you the performance. I mean, this is a theoretical performance out of our modeling analysis. The system parameter for us of writing our testnet is as follows. The partition factor C is chosen to be 0.01, and that's a knowledgeable guess. The block generation speed is 1,200 blocks per second. So that means our system is designed with the full capacity of 1,200 TPS. The milestone will be produced on average every 10 seconds, and this leads to on average roughly 12,000 regular blocks in each level set. Okay, so and here modeling assumption. The transaction arrival rate we assume is going to be 1,000, and we hope to achieve 1,000 TBS. And the percentage of malicious hashing power is assumed to be 30%. And here's the performance. So the queuing latency is around 3 minutes. The infection latency is half minute, and the secure latency is a bit longer. It's 800 seconds, and the wasted capacity will be 1.7%. So I want to emphasize that first of all, this is not a running result of our open testnet. This is a very loose upper bound estimate based on our modeling analysis. Of course, one thing I should mention is that how many blocks can we produce per unit of time really depends on the current internet infrastructure if we were to build a decentralized system. To summarize, today I have talked three things. First, a mechanism design based on structured DAG. Second is that involves also transaction assignment rule. Second is a reward scheme. And the third one is a fully specified algorithm that we hope that we can contribute towards solving these four issues that I mentioned at the very beginning of the talk. Of course, there are future research to do. First of all, we haven't discussed what's going to be the economic model. There are two aspects about that. So first is traditionally, are we going to use inflation model, or are we going to use a total limited supply model as in Bitcoin? But more importantly, there's a second issue, which is particular for a system with high TPS. So think about a system with high TPS. As I mentioned, if you build a system with 1,000 TPS, then data will be accumulated roughly at 10 terabytes per year. Okay, so far in our current blockchain technology, so we have produced a very good incentive to incentivize people to contribute to the consensus, I mean POW, right? But it's actually very expensive. These days, if we want to have such a system, storage and the bandwidth is very expensive. If you're trying to rent an Amazon server, it's going to be about $50 per month. But however, if you customize, if you expand the bandwidth and the storage, easily it goes up for more than $2,000 per month. Okay, so I want to make a point that the bandwidth and storage is very expensive. So for a high TPS system that requires high bandwidth and high storage, how are you going to incentivize players to contribute? Obviously via economic model, via incentive scheme, but this is future research. So second one is about optimization. For example, if the arrival rate of transactions is low, do we have to produce that number of empty blocks? Or can we adapt the rate at which total blocks being created in response to the changing arrival rate of transactions? So these are all very interesting research questions and that needs to be resolved. What I've talked about today has been written in our paper, being listed on our archive. You can download paper. I have to mention that this is joint work with my PhD student He Jiahao, Wang Guangju, and Zhang Guangyuan. So I have another team of very talented young people. They are, at this moment of time, they're still working very hard on a open testnet. So we have a number of servers that are generally supported by my university that's running our server room. And we hope to submit our code to GitHub very soon so that people around the world can clone the repo and run the code and join this open testnet. All right, that's all I want to talk about today. Thank you very much for listening.